So Saad, you're saying that when I switch to my document camera, it's showing up fine on the recording?
Yep.
You have no messages.
And I need to, I have to turn off my PowerPoint for that to happen, right? If I
That's
don't,
correct.
yeah, okay. If anyone has any questions about anything, this is a good time to talk about them. It can be about any topic.
Hey, Jeff.
Hi.
In this figure, it says you get this O6 phase when there's 24% lithium, but in your text it says 12%. Which one is it?
Where does it say 24%?
At the very top of the figure, it says lithium 24% occupation.
Yes. Well, if you look at it, only every second layer has lithium in it.
Oh, I see.
There's lithium here between these two cobalt oxide slabs, and if they're 24% occupied, then the next one has no lithium. That gives you 12% overall.
Okay, I see.
Pretty cool, right?
Yeah.
Jeff, I have a question about stacking.
Yep.
So is there any difference where you start counting the layers? You know, you start with the transition metal or you start with the oxygen?
No, there's no difference at all. You just can start however you want.
Okay.
So all it is a translation, right?
Mm-hmm.
Somebody's in the lobby. It's funny how sometimes it makes you admit people who are waiting in the lobby, and other times it doesn't. Do people think it will be useful for me to send the handwritten notes that I create like I did this morning? I think it might be easier than fighting through a video to find something.
I think
Yeah.
I think that's value.
Good.
Okay, I'll continue doing that. Okay, it's 12:35, so I'll begin. So I want to spend a bit of time talking about this O6 structure that forms as lithium is being removed from lithium cobalt oxide. So this phase forms around 4.55 volts versus lithium roughly. And it's really interesting to look at the stacking sequence, which is hard to draw just on this particular paper. So I've drawn it on a piece of paper already in the notation of hexagonal close packed planes, and I'll switch over to the document camera so you can see that. So I think now you should see the document camera, is that correct?
Yeah.
Yes, I don't want to spend the time drawing this, so I'm just going to put it on the screen for us to look at. So let me just fold it so I get it all on the screen at once. Okay, I think you should be able to see it now. So when you put the stacking sequence down, you know, A, B, C, A, you start with oxygen, you have transition metal on A, transition and oxygen on B, and so on. So this first pair of cobalt oxygen slabs that you see at the bottom, there's no lithium in between at all. And they are stacked with cobalts one on top of each other. This is what you find in O1, cobalt dioxide, or in titanium sulfide. When there's no lithium between the layers, it likes to be in this O1 sequence. And then in the structure, there's lithium in between every second pair of cobalt oxygen slabs. And those two, where the lithium is, they take the O3 type of stacking where the cobalts are shifted relative to one another. Now in this O6 structure, the lithium sites are only about a quarter filled randomly. So that's what this 24% means, is that this lithium site has a probability of being occupied of 24%. And it's probably actually 25%, which would make a lot more sense based on where the lithium atoms can go in between the layers. And we'll talk about lithium ordering and these fractions like a third, a quarter, a seventh, and so on later on in the class. But I think it's a really cool structure because it combines what we know about cobalt dioxide, which is lithium cobalt oxide that's empty, which is O1, and what we know about lithium cobalt oxide with all the lithium in, which is O3 type. So it's really cool the way this structure goes. So I'll send you guys this drawing by, I'll scan it later and send it with some other pages too today. Okay, so any questions about this? All right, hearing none, I'll go back to the PowerPoint. Okay, so you should see the PowerPoint again. So now I want to talk about the spinel material. So this is Li2Mn2O4, and this is formed by taking what's called LMO in our jargon, and LMO is lithium manganese 2O4. So if you take LMO and add further lithium to it, you get this structure, Li2Mn2O4. And it's a cubic unit cell outlined by these lines. It's a cubic box of lattice constant 8.2 angstroms. And the atoms within this box are shown. Oxygen is red, manganese is blue, and lithium is green. And the thing is, when you look at a structure like this, which is what you'll find when you open a website online, you look at it and you say it bears no relation to the layered structures we've seen before. And the point is, it actually bears an incredibly close relationship to the layered structures we've seen before. So I'm going to use Vesta to try to show you in a minute or two how this works, okay? But first, I'll just show you some Vesta diagrams statically. So if you take that cubic structure and rotate it so that the body diagonal of the cube is vertical, so you can see the cube, the outline of the cube. You put the body diagonal of the cube vertical, lo and behold, all the oxygen atoms are in layers. And if you were to look down from the top, you'd see that these oxygen atoms were close packed layers, just like before. And if you look at the way they're stacked, the oxygens, they go, if this is A, then this is B, and this is C, and you go back to A again. So the oxygens are A, B, C stacked. And that is exactly the way the oxygen atoms in lithium cobalt oxide are stacked. They're stacked A, B, C, A, B, C, and so on, okay? So the oxygen atoms in spinel, the spinel structure, have the exact same arrangement as the oxygen atoms in the layered materials like lithium cobalt oxide and lithium nickel oxide and NMC and so on. And now if you look at the planes in between these oxygen atoms, for lithium cobalt oxide, you would have a plane that was completely full of cobalt, and then a plane that was completely full of lithium. But here what you have, it turns out, is a plane that's 3/4 full of lithium and 1/4 full of transition metal, and then a plane that's 3/4 full of transition metal and 1/4 filled with lithium, and that repeats. Okay, so it's really similar to the layered structure, except the metal layers aren't pure lithium and pure transition metal. They're arranged differently. So this is a good time to pull up Vesta to show you the consequences of the way that the transition metals and the lithium are ordered in this material. All right, so I'm going to do that now. So I'll try to share Vesta. Oh, where is this? Oh my God. It's open on my desktop, but why isn't it showing up here? Okay, here we go. Right. Okay, so let's take a look at this spinel. So here's the spinel structure, and if we put appropriate polyhedra around the transition metal oxygen octahedra, this is what we see. And if you rotate this thing a bit, you can notice that there are tunnels for the lithium atoms shown here. It's an empty tunnel that they can move through. And in this layer, which is slightly tilted, there would be 3/4 filled with lithium and 1/4 filled with transition metal. And in the next layer up here, it's 3/4 filled with transition metal and 1/4 filled with lithium. And the oxygens are these big red ones. Now watch what happens when I rotate this thing. There's another set of tunnels. Okay. And it turns out that this structure has a three-dimensional connected network of tunnels. There's tunnels that are parallel to the x-axis, the y-axis, and the z-axis, all three. Okay. And that means lithium diffusion in this material is incredibly fast. It's a three-dimensional material. And this was the material selected by E1 Moly at the very beginning to make the first lithium-ion power tools, because it can support very high power discharge rates. Okay, so it's a really cool material. It has a structural relationship to the layered materials, but it also has this three-dimensional network of tunnels for the lithium to go in and out of. So I have no idea what you guys see when I'm rotating this thing, if there's a lag or whether it's pretty much in real time. How about if somebody comment on that?
It's in real time, it seems.
That's awesome. That's really good. Gotta love Teams. Okay, so this is the material that you get when you take LiMn2O4 and add another lithium to it to make Li2Mn2O4. If you want to see what the original spinel looks like, I'll show you that now. So here it is, and the cubic unit cell box is outlined, and we could rotate this thing to highlight the oxygen layers again. We'll try to do that. You don't really have too much control. There we go. Yeah. So here you can see the layers of oxygen. And now the lithium in this material occupies tetrahedral sites, not octahedral sites. So it's no longer in the center of the tunnel. It goes off to the side. And I think 1/4 of the tetrahedral sites are occupied now. And it's very similar to the situation that I talked about before, where, you know, there's this change of the site occupancy from octahedral to tetrahedral, just depending on what's more energetically favorable. So when you add more lithium to this system, the lithium leaves tetrahedral sites and goes into the octahedral sites, which are centered in the middle of the tunnel. It's pretty cool. And if you take all the lithium out of this material, these tunnels are completely empty, as you might expect. And you can take all the lithium out, and the tunnels do become completely empty. Okay, so any questions about this?
Yeah, Jeff.
Yeah.
I don't know if that's beyond the scope of this lesson, but would the diffusion rates change if it's in tetrahedral sites versus octahedral sites?
I think the answer to that is probably not very much, because to go from one octahedral site to the next, you have to hop through a tetrahedral site anyway. And to go from one tetrahedral site to the next, I think you have to go through octahedral sites. So I don't think it would change too much. I'm guessing.
Okay, thanks.
Yeah.
And sorry, so I didn't quite catch that, but you can fully delithiate this one. You can take all the lithium out.
Correct. You can remove all the lithium, and then these tunnels are empty.
Okay.
And the structure is completely stable without the lithium inside.
So just
Okay. Yeah, go ahead.
based on this structure, would it be safe to say that the spinel materials would have a lower capacity compared to the layered material, but they're useful for high power applications? Or is that not? Or do they have similar capacities to the layered oxides?
If you have a spinel material that you can make with all the lithium in, and you're cycling between lithium 0 Mn2O4 to lithium 2 Mn2O4, then it would have the same specific capacity as the layered compound. But when you try to cycle over that full range, structural degradation occurs in these materials. They cycle pretty reversibly between 0 lithium and 1 lithium. So the structure shown here with the lithiums in the tetrahedral sites. It turns out that when you put 2 lithiums into this structure, and put the lithium in the octahedral sites, all the manganese becomes 3+, and that causes a Jahn-Teller distortion in the material that it makes a big distortion, and it starts to crack apart. Now you're going to learn in a minute that there are other materials that take on this structure. Okay, once we go back to my notes in a little while. But I want to go back to the PowerPoint for a second. Okay, so let me make this minimal. And share the PowerPoint again. There we go. So let's see what's next. Yeah, so you have this picture shows the tunnels. And we talked about this. I'm not going to describe the stacking sequence as it says here. So this is a 1-1-0 projection of the hexagonal cell of the material that's LiMn2O4. And you can see the lithium in the tetrahedral sites. How do you know it's a tetrahedral site? You know it because it's directly above an oxygen atom. So these 3 are part of the 4 that form the tetrahedron. The 4th one is just kind of hiding back behind this guy. Or maybe it's hiding behind this guy. It's hard to be sure. We've seen that. Don't want to talk about that. This is what it looks like with all the lithium gone. Another picture of all the lithium gone. Okay. So now this is really important. How are the layered spinel and rock salt structures related to one another? So I spent the time this morning drawing a diagram to show how this works. And I'm going to put that on the document camera. And again, I'll scan it and send it to you. Okay, so we'll go to the document camera for a second. I think you should see the document camera now, is that correct?
Yes.
Okay, so now I'm bringing in my fabulous diagram, which may or may not be so fabulous, but I hope you can see it. So I've started over on the left side with O3 lithium transition metal oxide. So this could be lithium cobalt oxide, lithium nickel oxide, NMC, NCA, and all of this. And we've talked about the structure. It has metal oxygen slabs, oxygen, metal, oxygen, and then a pure lithium layer, okay? And in this case, the lithium can only diffuse in the layer. It can't move from one layer to the other. So this is two-dimensional lithium diffusion in this compound. Spinel has exactly identical oxygen positions. If you look at the oxygen, they're the circles. They're exactly the same as O3, identical oxygen position, no change. And the difference is that instead of a pure metal atom layer, you have a layer of cations that's 3/4 metal and 1/4 lithium. And they're arranged in an ordered way so that you get those tunnels that I showed where the lithium occupies the sites along the tunnels. And then the next metal layer is 1/4 metal and 3/4 lithium, all right? So these two materials aren't very different at all. Now you may wonder why we never talk about lithium manganese oxide. Why don't we talk about it? I mean, manganese is way cheaper than cobalt and nickel. Why don't we make lithium manganese oxide in the O3 structure and use it?
It converts to spinel during cycling.
It converts to spinel during cycling. And how easy is it for it to convert to spinel? Well, all that has to happen is some manganese atoms from the metal layer have to drop to the lithium layer. That's a motion of 3 angstroms. 3 angstroms for an atom to move. That's not very far. And the lithium goes back into its site. So layered lithium manganese oxide is just not the stable form. Spinel is the stable form. So you can make it like this, you can trick it and make it, but it will convert to spinel while it's cycling, and it has lousy properties. There are other spinel compounds of interest. For example, if you make lithium cobalt dioxide at low temperature, around 400 degrees C, it actually takes on the spinel phase. So it's written as lithium LiCOO2, but you would write it as Li2CO2O4 if you're talking about the spinel phase. And then there's a very famous negative electrode that we'll talk about in the negative electrode section called lithium titanium oxide, LTO. And when LTO is in the fully lithiated state, it has this stoichiometry, Li7/3 Ti5/3 O4. So if it just 7/3 is 2 1/3, and 5/3 is 2 minus 1/3. So what it means is there's 1/3 of the lithiums on the titanium sites, but it takes the same structure, the spinel structure. And in these materials, the lithium and the metal are ordered to create tunnels for lithium. 3-dimensional interconnected tunnels. Generally supports high rate. Okay, then what is rock salt? Well, rock salt is the sodium chloride structure. And these materials, lithium transition metal oxides, will often take on a disordered rock salt structure, where the number of cations is equal to the number of anions. So if you take 1 minus x plus x, you get 1. So there's 1 cation per anion. That's what happens in the rock salt structure, 1 cation per anion. But if you look at the way the oxygens are arranged, they're exactly the same as in the layered structure, the spinel structure, and the rock salt structure. They're identical. The oxygens are identical. And if you look at the metal atom layers, if the overall stoichiometry is as shown in this case, the metal atom layers have 1 minus x lithium and x metal. So say x was 0.5, every layer would be half lithium and half metal. And they would be randomly arranged on the metal atom sites. And there's a lot of, pretty famous materials in this class. So an example would be if X is equal to 1, you could have nickel oxide or cobalt oxide. They take the rock salt structure. You can have situations where you make a situation where you have lithium nickel oxide with, I don't know if I have the number here right here. It should be less than 0.32, sorry. You have lithium deficient lithium nickel oxide, and it becomes disordered rock salt. And again, you find on the surface of materials like NCA, lithium nickel oxide, their surface often has a layer of rock salt on the surface, which doesn't mean nickel oxide, it means lithium deficient lithium nickel oxide on the surface. And to go from the layered structure to the rock salt, all it means is that there's some transition metals and lithium's mixed up. They're not in the perfect arrangement. They should be in the layered structure. They just get mixed up. So I think it's really important to understand structure from this point of view, to realize that the oxygen atoms are exactly the same in all these materials, and all you have to do to go from one to the other is move some cations around. And in these materials, because the atoms are randomly positioned, typically the diffusion is very slow because there aren't tunnels and there aren't layers for the lithium to just move along. There's always transition metals in the way that are bumping into them and messing up the diffusion paths. Okay, so any questions about this?
Yeah, Jeff, how common is it to have O3 rock salt structure versus an O1 rock salt structure?
There's never been an O1 rock salt structure because rock salt is cubic, and to get a cubic structure you have to have cubic close packing, and O1 is not cubic close packing of the oxygen. Is that okay for an answer?
Yeah, I think I was mistaken.
But that's a good point. That's a really good point, because if you take, I think I come to this in the PowerPoint in a minute or two, if you take a structure like O2, lithium cobalt oxide, it has a different oxygen stacking than O3. Well, what will the surface phase be on O2 lithium cobalt oxide? Will it be rock salt, or will it be some weird thing? I don't think anyone's ever looked. That would be kind of cool to do. All right, so let's go back to the PowerPoint, unless there's more questions on this slide.
Is it possible to have a lithium aluminum oxide without other transition metals? And what structure would that have?
Lithium aluminum oxide is O3.
Cool. Thank you.
Okay, so I'll go back to the PowerPoint again. Yeah, so this is actually very cool. So this is a paper that Jim Lee wrote. Jim is now at Tesla, and he did it in collaboration with the people at the Canadian Center for Electron Microscopy. So Hansho Liu was a graduate student there, and everybody else was in our group except Gianluigi Botten is the head guy at the Canadian Center for Electron Microscopy, and he's also the director of the Canadian Light Source now, so he's a big guy. Anyway, if you do these TEM images where you try to image you align the crystal in such a way that you can see the layers of transition metals, which are these dark ones. Excuse me, these bright ones. And then in between, you barely see the lithium in between. And then as you move to the surface of the material, everything looks the same. And that's because there's a layer of rock salt at the surface. And remember, rock salt doesn't have pure metal layers and pure lithium. They have layers of equal transition metal content in every layer. So, I mean, isn't that incredible? It's really incredible. And the oxygen atoms aren't shown in this diagram, but you have this structural continuity between the layered and the rock salt phases because the oxygen lattice is exactly the same. It's beautiful. Hopefully
Hey,
that makes your day. Yeah.
Hey Jeff, what is the reason the oxygen is not shown? I think the oxygen actually have larger size since it's ionine of the crystal structure.
I can't answer that question. I don't know enough about electron microscopy to tell you why the oxygen doesn't show up.
Okay.
Yeah. We don't have to look at this. Okay, so.
Can I make a quick comment about the oxygen?
Yeah, sure.
I'm not an expert either, but I think it has to do with the nucleus of the atoms. So oxygen is 16, but the transition metals are 55, around there. So they should be more visible to different radiation, like X-rays and stuff.
Yeah, so maybe what we're seeing here, Ron, is in the lithium layer, we're seeing a little bit of transition metals still. And only when you get deep inside, you don't see anything in that lithium layer. So maybe what we see here is small amounts of transition metals that eventually become no transition metals as you move in. Do you think that's possible?
I think so.
Okay, so let's say that Ron knows what he's talking about. Okay, so this is an interesting paper. This is from a long time ago. And this is because this paper got created because we realized that many of these different lithium transition metal oxide structures shared the exact same oxygen lattice, this cubic close-packed oxygen lattice. And there were different structures, lithium nickel oxide, layered lithium oxide, cobalt, spinel cobalt oxide, Li2Ti2O4, this is spinel structure, and this gamma lithium iron oxide structure has the lithium and iron arranged in some strange way. But all of them share the same oxygen lattice. And what Wu Li and Jan Reimers tried to do is try to understand, why do they form the different structures that they form? And could you understand it based on what's called a lattice gas model? And we'll talk about lattice gas models for, I don't know, 3 or 4 lectures later on in the course. But anyway, what they show you here is the way the cations are arranged in each of these structures, where there's an equal number of lithium atoms shown as open circles and metal atoms shown as dark circles. So in spinel, if you look at the cubic unit cell, you see the way they're arranged. In the layered structure, the body diagonal of the cube is perpendicular to the layers of the metal atoms, which are highlighted with these triangles. In spinel, things are arranged like this, and you can see the way the lithium is in tunnels. And in this orthorhombic LiMn2 lithium manganese oxide structure, it's not spinel, it's not layered, it's not rock salt, it's some other arrangement. You again get tunnels of lithium. And this material works, but it converts to spinel. So it starts in this structure, which works okay. In a few cycles, it converts to spinel and shitty. Okay. So really understanding the fact that all these structures share the same oxygen lattice allows one to proceed and and make sense out of a lot of foolish things that you see or strange things that you see in experiment. So I really believe understanding structure is important, and that's why I'm harping on this so much. Okay, so let's talk about LiFePO4. So this is a picture of LiFePO4. It has an orthorhombic unit cell, shown by this rectangular box, and it again has tunnels for the lithium atoms to reside along. These shaded polyhedra that contain iron in the middle are FeO6 octahedra, and these other polygons, which are tetrahedra, these have phosphorus atoms in the center. These are PO4 phosphorus tetraoxide tetrahedra. And in between these iron oxygen octahedra and phosphorus oxygen tetrahedra, you find these tunnels that the lithium atoms can move along. Okay. Now it turns out that there's only tunnels along the B axis. So lithium LiFePO4 is a one-dimensional diffuser for lithium. And if you have just one iron atom that's in the middle of the tunnel by mistake, it will block the lithium diffusion. And this is one of the reasons why lithium diffusion in lithium iron phosphate is relatively poor, because any defects just completely screw it up. The lithium can't go around it like it can in a layered material. There's two dimensions in which it can move. Or in spinel, it has three ways it can get around a defect. Okay, so I want to show you in VESTA the way that LiFePO4 is related in structure to the layered materials. So let me go back to VESTA. How do I do that? I think eventually I'm going to get good at this. Where's VESTA? I don't see it. What's that? I might have closed VESTA, did I? God. What's this? Can you guys see my screen or not? Do you see VESTA at this time?
We can
No,
see
we
your
can see
screen.
your doc-
That's
What's that?
We can see your documents.
Oh. Okay, let me try to fix that. Okay, so I'm going to try to share. It'd be so nice if I could tell what you guys see. Do you see my Windows Explorer now?
Back to your documents again.
Back to my document camera?
No, that's
we
your
see
Explorer.
your Windows Explorer.
Okay, so I'm going to start the VESTA program. Do you see a lithium iron phosphate structure now?
I'm still
No.
on the Explorer screen.
Okay, let me try to figure out what's wrong. It's crazy. Just not giving me a chance to select VESTA here. Let me close a few windows, I guess. What's this? Okay, close this. Let me close something else. Now I'll try to share again. Can you see anything now? That looks like
Yep.
lithium iron phosphate?
Yep.
Okay, great. That's really comforting for me. Okay. So if you view lithium iron phosphate parallel to the AB plane, so you put the one plane of the rectangular unit cell horizontal, then you will see the oxygen atoms, they look like they're in layers, okay? You can see the oxygen atoms look like they're in layers. And if you look at the way the oxygen goes, if you were to look from the top, you'd see it was a triangular lattice, slightly distorted, of oxygens. So these are on the A sites, and then it's shifted over to B, then back to A, B, A. So this is hexagonal close-packed oxygen. So LiFePO4 is very different than the materials we've talked about up till now, because it's hexagonal close-packed oxygen, not cubic close-packed oxygen. And it's not perfect, okay? It's distorted, but it's sort of close. And then if you take this thing and rotate it so that the B axis points out of the page, you'll see the tunnels for lithium that are parallel to the B axis. You know, so learning how to use VESTA is really useful to be able to take a look at structures and think about them. But I also believe that knowing how to deal with them on paper using the notation of hexagonal close-packed planes is incredibly important also, if you really want to know what's going on. So pretty cool, right? Okay, let's go back to the PowerPoint. Okay. So I want to share the PowerPoint again, which is gone. Jeez, driving me crazy. Here it is. Okay, can you see my PowerPoint now?
Yep.
Okay, great, thank you. So we looked at this. I showed you that it was approximately AB oxygen stacking. And then this is another really interesting structure. It's lithium MO6 Se8. So here the seleniums are the yellow ones. The molybdenums are these small balls that are near the selenium, and the lithium are these, I guess they're green. I can't, you know, I'm colorblind. It could be any color, but it looks green to me. And this is a bizarre structure in that you have these clusters of MO6 Se8 here. It's a cluster. And then it's just linked from molybdenum to selenium next to the next cluster. So it has these clusters. They're almost cubes, slightly distorted cubes. And then in between them, or on the corners of the cubes, are where you find the lithium atoms. And what's interesting about this structure is the lattice constant is big. It's about 8.5 angstroms. So the near neighbor distance, the lithium-lithium near neighbor distance of this thing is about 8 angstroms. It's huge. With lithium cobalt oxide, the near neighbor lithium-lithium distance is 2.8 angstroms, so it's very close. Similar in spinel. Now, because these holes where the lithium can go are so massively huge, this particular structure can accommodate things like zinc and lead and big, massive cations. So it was used as a positive electromaterial for magnesium intercalation and magnesium batteries. And it worked very well. The other thing about this is that this class of materials was discovered by a guy named Roger Chevrel in France, and they're called Chevrel phases. So whenever you see something like MO6S8 or MO6Se8 or MO6 tellurium 8 with some kind of cation in front, that's a Chevreul phase. Now, because these holes for lithium are so massive, you can actually fit 4 lithium atoms in every hole. So the end stoichiometry is Li4 MO6Se8 or Li4 MO6S8. And the reason that this structure is interesting is because when you work between no lithium and 1 lithium, the lithiums are so far apart that one lithium doesn't really notice the other one. They're so far apart. Their Coulomb repulsion is incredibly tiny. So you can study a system where you can add lithium and they don't interact with one another at all. And then understanding how the voltage composition curve changes in such a situation is relatively simple compared to other cases. So I wanted to just show you this structure now because we'll talk about it later in class, and it's not used commercially at all, but it's really interesting scientifically. Yeah, so that's all I have on positive electrode material structures. And I think, you know, given that we're going to change to negative electrode materials in the next lecture, and we have 5 minutes left, it doesn't make sense to start that now. So I'll start that next time. So if there's any questions about this, now is a good time to ask.
I had a question, but it's more related to the homework.
Sure.
I think it's number 5, where you asked us to read a paper and summarize the importance. And the paper was on lithium manganese oxide with the O2 structure. So when it does convert to spinel, it says that it leads to rapid capacity loss. What is like the main contributor of the capacity loss there?
Yeah, I think the main problem with manganese oxides, when you try to cycle them with large specific capacity, so for example, go from 0 lithium to 1 lithium per manganese, is that you move into a range where you have manganese 3+, which is a Jahn-Teller ion. And that means that the oxygen octahedron around the manganese does not remain a symmetric octahedron. It distorts. So you move from a case where with no lithium you have a symmetric octahedron to a situation where with 1 lithium you have a distorted octahedron. And this just wreaks havoc with the structure, okay? And I think that's the main issue. Whenever you have a situation where manganese is going between 4+ and 3+ repeatedly, you can get into this kind of trouble.
Okay, yeah, and then that would lead to stress on the SEI, right?
Well, all kinds of issues.
Okay. Cool. Okay, thank you.
All right, so hearing no more questions, we'll call it a day for today, and I'll see you on Friday, and we'll start working on the negative electrode stuff. Okay? Goodbye, everyone.